Hey, welcome back. We just finished to talk about 239 sliding window maximum, and we're gonna continue our journey to Leetcode. We're gonna talk about a very similar problem with the 239 shortest subarray with the sum at is k. And let's go ahead and read the question. So we're gonna return the length of the shortest non-empty contiguous subarray of A with the sum at is k. And if there's no non-empty subarray with the sum at is k, and we're gonna return -1. And I think the example is pretty short, and let's find a slightly longer example. And we're just gonna fabricate some numbers right here. So for example, we have a whole bunch of numbers right here, and we are trying to find a sum of the subarray, and to make sure the summation of the subarray is greater or equal to k, and we want to have the shortest length of the short subarray. So how should we do that? And the tricky part of this problem is that we have some negative elements. So let's assume that if all the elements within this subarray or within this array is all positive, and to do that is pretty straightforward. So we're gonna have a um, two pointer, and basically we just move forward, and once we have the summation within this range is greater or equal to k, and we can start like moving uh the left pointer, and then once we move that, and then once we have the summation is less than k again, and then we start moving the right pointer and keep going forward by using on time complexity to solve the problem. So that's the case is that when we only have the positive elements or positive or zero in elements within this array. But now the case is that we have negative elements within this array, so we cannot use that. Um, so how do we do that? I mean, to think about this problem in the brute force way, so we can use all the combinations between uh, I and j. We still have the 2 pointers, and I and j can be all the combinations between this array, and we can just calculate the summation, and then we just make sure the summation is greater or equal to k, and then we just calculate the length of this. That's doable, and that's gonna be n to the cube. And there's one optimization we can make on top of the brute force is by using the prism. So we can do the prefix summation, and so we can easily use O1 complexity to calculate the summation between each individual range, and then we can also calculate that. So that's gonna bring down the complexity to n squared, and this is not gonna pass because we have a really huge range right here. So 10 to the what is that? 5 times 10 to the fourth power, and square is gonna be almost into 10 to the ninth power. Not gonna pass. And how do we do that? So how do we bring down the complexity? And one way to bring down the complexity is by using still heap or multi-set or tree set to do that. I mean, first we do the prefix summation. So we do the prefix summation, and let's assume that a capitalized X is going to represent those numbers with the prefix summation, and we fix one element. So the right pointer j, each time within the sorted data structure, for example, tree set or multi-set, and we're gonna find an index that fits the needs, and we can find an x that the between the and then to make sure that we want to find an index to form the summation of this range is greater or equal to k, and then so we can calculate that as well. So that's one solution, and but that's not the optimal solution. So the optimized solution we're gonna talk about right here is gonna be similar to problem 239, which we just discussed a few minutes ago. All right, so the way we deal with the 239 is sliding window maximum, and now we convert the entire array into something called prefix summation. And based on the prefix summation, and we can translate this problem to 239. How do we do that? The way we do that is, so we want to maintain a DQ as well, and the DQ is increasing order. So why do we do the increasing order? So I'm just gonna explain. But before we could dive into like we popping from the right hand side, let's go ahead and talk about the similar approach with the 239, which is popping from the left hand side. And if you remember the 239, and we just talked about it a few minutes ago, and basically if the new elements is adding from the right hand side, we're gonna pop the elements from the left hand side. And very similar approach from this problem is that once we have the new elements is being added into our sliding window, right? So for example, we have 3, and now we're gonna incorporate the next element. And once we have the new elements is being incorporated, and at here on the left hand side, we always wanna popping out from the left hand side. So just like the 2-pointer solutions, right? So if we have the 3 elements is already fits the needs, and the summation of the 3 elements is already greater than k, and we actually want to start popping out from the left hand side because we want to find the minimized length, and we know that if we are adding one more element in it, and that's gonna make the subarray longer. So we don't want to make the subarray longer. We want to make it smaller. So that's why we start popping out from the left hand side. Once we fix the needs that the summation of the subarray is greater or equal to k, and we start popping the left hand side. So if the 3 elements from here with the new elements being added from the right hand side is still greater than k, and then we don't need this guy as well. And we're checking these 2 elements. If these 2 elements is still greater than k, and we just keep going up, and but you got the idea. Basically, we need a while loop to checking that. So that's from the left hand side. And how do we do that from the right hand side? The way we do it from the right hand side is we want to keep the queue increase in the increasing order. So why do we want to keep the queue in the increasing order? So pretty much we know that this is the prefix sum. I can't pronounce the word right now. Prefix summation array. So basically, for example, we have 2, 3, 1, 4, -1, and 5, and the prefix summation is gonna be 2, 5, and 6, and 10, and that next one is gonna be 9 and 14, and so pretty much like all of this is gonna be increasing, but once we see this guy, we know this is a decreasing order. So this decreasing order, we're gonna kick this guy out, and just like the 239. So once we see the smaller number, we're gonna kick this guy out. But why do we want to kick this guy out? It's because 10 all the way to here. So the reason we do that is because we have 9 here, and for example, we have 10 here. We know this is decreasing. So it doesn't make sense that, for example, we start calculating from the right-hand side right here, and then like on the left-hand side. So you see a number that is greater than u, and you know that the summation from here is wasted. So this guy is greater than this guy, and then this is -1, and so it doesn't mean anything because we know that k is going to be a positive number. So that's why we're just going to remove this guy. We're not even going to consider that guy. And then we're just going to use this at the right hand side. And once we subtract here, for example, and I subtract 4, 5, it's going to be a positive number. So we don't waste our time to calculate a negative number in this range. That's pretty much like the cases. So we either pop from the left hand side or we also pop from the right hand side. So when we pop from the left hand side, so basically we are shrinking the range of the length. So you know what, I'm just gonna write the code, and so let's understand that while we write the code. So basically we still need a DQ, and just like the last problem, and in this case we are gonna store 2 things. One is this prefix summation, and another thing is gonna be the index. So instead I'm gonna store a tuple. So that's why the initialization we're gonna put in is gonna be 0 and 0, and the first 0 is gonna be index, and the second 0 is gonna be the summation. So you'll see the differences later. So now we have the prefix summation, and we put for loop in it, and we're gonna start doing the for loop, and we are looping through the entire array. So that's gonna be a, and each time we're gonna accumulate the summation. So sum is gonna plus or equal to the num, And once we have that, and we start popping out from the left. So even though it's not really intuitive because we haven't start appending into the queue, so in your mind it's probably empty, but let's pretend that, you know what, let's do append first. So let's append, and because these are zero index, right? So we need to plus one, and sum. So sum which we calculated right here, and now we can start like popping from the left hand side. So once the case is when I pop from the left hand side is when we fix the position, we fix the need, and the condition is gonna be the zero and what is that? The summation is the second element, so we put one right here. So if the difference is between the current summation and the prefix summation in the very beginning, if the difference is greater or equal to k, that means we fix the need and we fix the condition, and then we're gonna start popping from the left. So before we popping from the left, then we're gonna calculate store the results. So we actually need to store the result as well, and because we need the smallest elements, right? Smallest the length, so that's why I need a positive infinite number right here, and we're gonna calculate the smallest number. So we take the result and we take the I minus what? Minus the index. So what's the index? That's the first element of the first node in the queue. And so we minus that and we plus one. The reason we plus one is that, for example, we have one here, we have zero here, and one minus zero, and doesn't represent two elements, right? So we have the plus one. So that means we have the two elements right there. Once we have that, and then we start popping from the left hand side. So just like the regular 2 pointers, and you have the left pointers and start accumulating to the right hand side. So once we pop that, and the first elements become the pointer actually moved to the right hand side. So that's what we're doing. Somehow it's being removed. Okay, that's when we deal with the left hand side, and same thing we're gonna deal with the right hand side. And this is a slightly different with the 239, right? 239 when we deal with the left hand side is that because we only add one element from the right hand side and we pop from the left hand side, and we just use the if condition, but now we use a while loop. So while loop, the reason we use while loop is that the condition changed. It used to be index based. In the 239, we actually just want to keep the window sizes the same. But right now, we just want to keep the value the same. So values might be varied, right? Some numbers might be big and some numbers might be very small, and that's why we use the while loop to keep track of that. And we're gonna have the queue, and then we also want to maintain the increasing queue. So the way we deal with the increasing queue is that if the newest element, the summation, right? So if you're incorporating a new number, and if the new number is less or equal to the last elements from the queue, that means the new number you're incorporating is the negative number. So we don't need the previous numbers anymore. So we just popping those guys out. And because we want to have maintain an increasing queue, and the way we do that is popping everything previously out. And so once we have that, and we start appending what we have, right? I think we're done. So all we do is return the value. So the way we return that is if result is less than float infinite. So that means that we did updates the value. So then we just return result. Otherwise, we're gonna return -1. And let's try if that works or not. Okay, works. Yeah, so basically very similar to 239. So all we do is tracking from the left hand side and from the right hand side. And if you understand the logic, so I think you got it. If you like the video, please subscribe to the channel. I'll see you guys in the next video.